Hello students, welcome to our physics class. This is current electricity part 13. In the previous class, we learned about potentiometer, meaning construction and working, and one application of potentiometer, that is comparison of EMF of two cells. Comparison of EMF of two cells. So in this class, we are going to discuss about the next very important application, that is determination of internal resistance of a primary cell using potentiometer. So this is the last part of this chapter. Okay, well, let's start today's class. So this is the second a very important application of potentiometer, determination of internal resistance of a primary cell using potentiometer. So this is the circuit diagram. So this circuit diagram is used to find the internal resistance of a primary cell. So what is the meaning of potentiometer? Potentiometer is a device used for measuring an unknown EMF or the potential difference accurately. The potentiometer consisting of a long wire AB, that is of length 1 meter or 4 meter or 10 meter. So here we are using 4-meter wire potentiometer. So actually the 4-meter is cut into 4 equal pieces. So those pieces are arranged in parallel and connected in series by using thick copper metallic strips. Why thick copper metallic strips are used in potentiometer for connections? Because thick copper metallic strips do not contribute any resistance in the potentiometer wire. So the wire is made of manganese or constantan, because manganese constantan having very high resistivity and very low temperature coefficient. So 1 meter scale is fixed parallel to the wires. So after that, a cell, a plug key, rheostat, all are connected in series, and this series combination is connected across A and B. So what is the meaning of rheostat? Rheostat is a wire wound resistor. Its resistance varies from minimum to maximum. Actually, rheostat varies the current and voltage in the circuit. That is the function of rheostat. So this is plug key. It switches on or switches off the circuit, making or breaking the circuit. The battery means the combination of cells. So this is the primary circuit of so this one is the primary circuit of the potentiometer, and this is necessary for all potentiometer experiments. So this is called the primary circuit or driving circuit or auxiliary circuit. So this is the secondary circuit. So this is a primary cell, and this is positive terminal of the cell. This one is the negative terminal. The positive terminal of the cell, that is connected to point A. Negative terminal is connected to a galvanometer and the sliding contact. Negative terminal is connected to galvanometer and the sliding contact. So after that, a resistance box is connected across the cell through a plug key. Okay, that is K2. So this is the secondary circuit. So now let us start the experiment. So the experiment is very simple. Actually, so this experiment has two very important parts. So in the first part, K1 is closed, K2 is kept open. K1 is closed, K2 is kept open. So this is the first part of the experiment. So what we have to do, K1 is closed and K2 is kept open. Okay. So after that, check the connections. If the jockey that is connected at point A, jockey is pressed at the point A, galvanometer shows a momentary deflection in one side. So after that, jockey is disconnected at point A, connected at point B. Jockey is connected at the point B. So then galvanometer shows a momentary deflection but in opposite direction. So if the jockey is connected at point A, galvanometer shows a momentary deflection in one side. If the jockey is connected at point B, galvanometer shows a momentary deflection but in opposite direction. So that clearly shows the circuit connections are absolutely correct and there is no fault in the circuit. So after that, jockey that is gradually moved. Jockey is gradually moved where on potentiometer until the galvanometer shows null deflection. The jockey is gradually, as the jockey is gradually moved where on the potentiometer Y. So until the galvanometer shows the null deflection. So if the galvanometer shows null deflection, then the potential difference across AJ1 that is exactly equal to the potential difference across the cell. Okay, here A, E, G, J1A. So this is a closed conducting path. So let us consider the distance from A to J1. Okay, that is L1. So now apply the Kirchhoff's voltage law to the loop A, E, G, J1A. What is the statement of Kirchhoff's voltage law? In a mesh of an electrical network, algebraic sum of product of current and resistance in different parts of the mesh that is equal to algebraic sum of EMFs in that mesh. So here algebraic sum of product of current and resistance, that is 0 because in this loop there is no resistance. And so actually here The current always drawn from the positive terminal of the cell. This is I. Okay. So this is anti-clockwise EMF. So the wire of potentiometer act as a source of variable voltage. So now the potential difference across AJ1, potential difference across AJ1, potential difference across AJ1, that is equal and opposite to the potential difference across the cell. Potential difference across AJ1, that is equal and opposite to the potential difference across the cell. Actually, this is anti-clockwise EMF and this one is the clockwise EMF. So E is taken as positive and this one is taken as negative. That is potential difference across AJ1. It is minus V1. So E is equal to V1. What is the principle of potentiometer? When a constant and steady current flowing through a wire of uniform cross-sectional area and composition, the potential difference across any length is directly proportional to that length. So V is equal to KL. K is potential gradient. Potential drop per unit length of potentiometer wire is called a potential gradient, and this is the principle of potentiometer. What is that? When a constant and steady current flowing through a potentiometer wire having uniform cross-sectional area and composition, the potential drop across any length is directly proportional to that length. So V is proportional to L, V is equal to K. So what is the value of V1? That is K L1. E is equal to K L1 and call this as equation number 1. Okay, so this is the first part of this experiment. And go to the next part. Second part. So again, the procedure is same. First, the jockey, but in this case, both K1, K1 and K2 are closed. Both K1 and K2 are closed. So after that, jockey is connected at the point A. Galvanometer shows a momentary deflection in one side. Jockey is connected at point B. Galvanometer shows a momentary deflection but in opposite direction. And after that, jockey is gradually moved on potentiometer wire until the galvanometer shows null deflection. So compared to the first part, in the second part, the balancing length is less. L2 is less than L1. So why? So this point is very important. Second part, the balancing length L2, that is less than L1. What is this? L2. L2 is less than L1. because now both K1 and K2, so both K1 and K2 are closed, and a suitable resistance that is introduced in the resistance box. So now the cell is in closed circuit. The potential difference across the cell, that is actually called the terminal potential difference. So in the first part we will get the EMF. EMF means the potential difference across the terminals of the cell. The cell is in open circuit, but here the potential difference across the terminals but the cell is in a closed circuit. That is not EMF, that is terminal potential difference. So EMF is always more than the terminal potential difference. So that is why the potential difference across AJ1 is much greater as compared to the potential difference across AJ2, because the EMF of the cell is always more than the terminal potential difference. So now the potential difference across the cell and potential difference across AJ2, their magnitudes are same, but direction is quite opposite. Now again apply the Kirchhoff's voltage law. So apply the Kirchhoff's voltage law to the loop, that is A, E, G, A, E, G, J2, J2A. So LHS part, so algebraic sum of product of current resistance, that is 0. RHS part, actually one is the anti-clockwise EMF, another one is clockwise. So this is terminal potential difference. Let us take, that is V. E is EMF. EMF of cell means potential difference across terminals of the cell. So when the cell is in open circuit, so this is terminal potential difference, means potential difference across the cell. The cell is in closed circuit. So V minus V2. So V is equal to V2. So V is equal to V2 is KL2. So V is equal to KL2. So call this as equation number 2. Okay. Now equation 1 divided by equation 2 implies that equation 1 divided by equation 2 implies that E divided by V, that is equal to K L1 divided by K L2. So K get cancels and we will get E divided by V, that is equal to L1 divided by L2. So what is the relation connecting between electric current, external resistance, internal resistance, EMF, that is I is equal to E divided by R plus R. So EMF of the cell is I of R plus R, and the terminal potential difference across the cell, so that is V is equal to I into capital R. So this is according to Ohm's law. So this is Ohm's law applied to a closed circuit. So EMF value I of R plus R, terminal potential difference IR. So that is why EMF is always more than the terminal potential difference. Okay. Now the equation becomes, what is the value of E? E is I of R plus R divided by V is I into capital R. That is equal to L1 divided by L2. So I get cancels. So R plus small r divided by capital R, that is 1 plus small r divided by capital R, that is equal to L1 divided by L2. So, and small r divided by capital R, that is equal to L1 divided by L2 minus 1. So finally we will get the expression for internal resistance of a cell, small r is equal to capital R into L1 divided by L2 minus 1. So this formula can be used to find internal resistance of a primary cell. Small r is equal to capital R of L1 divided by L2 minus 1. Right? Now capital R is noun, L1 is noun, L2 is noun. By using this formula, the internal resistance of primary cell that can be easily calculated. So this is about the determination of internal resistance of a primary cell using a potentiometer. So what is the meaning of internal resistance of a cell? The opposition offered by cell to the flow of current. The opposition offered by cell to the flow of current is called the internal resistance of a cell. So what are the factors affecting the internal resistance? Internal resistance of a cell is directly proportional to the separation between electrodes and inversely proportional to area of immersed portion of electrodes. So finally we will get R is equal to CL divided by A. So it depends on the concentration of electrolyte, separation between the electrodes, and area of immersed portion, of electrodes. And the internal resistance is measured in terms of ohm. What is the SI unit of internal resistance? That is ohm. What are the factors affecting? So it depends on the separation between the electrodes, area of immersed portion of electrodes, concentration of electrolyte. So what is the meaning of internal resistance of a cell? Opposition offered by a cell to the flow of current, or the solution of a cell causes a certain hindrance to the flow of current. The solution of a cell causes certain hindrance to the flow of current is called the internal resistance of a cell. Okay. Thank you.